This is eigenvalues. So we are trying to find the eigenvalues and eigenvectors of some matrix. This is problem 8.8.13 in the textbook. Because eigenvalues can get a little confusing, I'm going to also go over some of the theory behind what an eigenvalue and an eigenvector is. So when we're trying to find the eigenvalues, we have some matrix A, and we want to know, do there exist some vectors k and scalars lambda such that multiplying a times k has the same effect as lambda k? In other words, are there some vectors where multiplying the vector by our matrix A has the same effect as just scaling the vector? And so we start with this equation here, and we really can derive everything else from this equation. So because ak is lambda k, we can, of course, always write this scalar multiplication as lambda I. So this is ak equals lambda times I, the identity matrix, times k. And then we can subtract this from both sides, because this is a matrix of the same size as A. And so AK minus lambda I k is 0, or the 0 vector. And so we can factor out k from this, because it's a vector, we'll factor it out on the right. And so we have A minus lambda I, which is a matrix equation, times k, a vector, is 0, the 0 vector. And then we do two things with this. We do something with this to get the eigenvalues, lambda, and we do something else to get the eigenvectors, which are k's. And so to find the eigenvalues, if this equation is true, then the determinant of this matrix, A minus lambda I, must be 0. So we know that the determinant of A minus lambda I is 0. So we can use this to find the eigenvalues, because we know how to compute the determinant. And to find the eigenvectors, since this is a matrix algebra equation, we can just solve it like we would any system of linear equations. We'll have to solve it multiple times because we'll have multiple different values of lambda, but that's fine. We know how to do that. So let's go ahead and find the eigenvalues. So to find the eigenvalues, we know that A minus lambda I equals 0. Let's go ahead and write down what A is. So this is A. A is 480, negative 5. And then we'll also do lambda I. So I is the identity matrix. Since A is 2 by 2, I will be the 2 by 2 identity matrix. So I is 1, 0, 0, 1. Then lambda I will just be lambda 0, 0, lambda, because we just multiply this matrix by lambda. And so A minus lambda I will be 4 minus lambda, 8, 0, negative 5 minus lambda. So now we can compute the determinant of this. So determinant of A minus lambda I is the determinant of 4 minus lambda, 8, 0, negative 5 minus lambda. And we know that that's equal to 0. So let's expand out this determinant, and then we can solve this for lambda. So if we expand out the determinant, we get 4 minus lambda times negative 5 minus lambda minus 0 equals 0. So that means that 4 minus lambda times negative 5 minus lambda equals 0. So then either 4 minus lambda is 0, And so lambda is 4, or negative 5 minus lambda is 0. So lambda is negative 5. So lambda is either 4 or negative 5, and actually both 4 and negative 5 are eigenvalues. So I will call 4 lambda 1 and negative 5 lambda 2. That's important because we need to associate each eigenvector with its own eigenvalue. And not all eigenvectors will share eigenvalues. There are some cases where they do, but you always want to number both the eigenvalues and eigenvectors and keep the numbering the same. So eigenvector k1 is associated with eigenvalue lambda 1, which just makes things easier in the long run. Okay, so we have the eigenvalues. Now let's go find the eigenvectors. So to find the eigenvectors, we'll just construct this system of equations, a minus lambda I k equals 0. And we'll actually have two separate augmented matrices for this. So we'll have the one for lambda equals 4, so lambda 1 is 4. So this gives us the augmented matrix a minus 4I bar 0. And then for lambda 2 is negative 5. So this gives us the augmented matrix a minus negative 5I bar 0. So for lambda 1, which is 4, a minus 4I is the matrix 4 minus 4 is 0, 8, 0, negative 5 minus 4 is negative 9, bar 0, 0. And so from here, we can see that this is just a system of linear equations. So if k1, let's represent k1 by k1, this is the eigenvector k1, that will be k1, k2, 1, 2, 3, wait. Hey, go out, I'm recording. Okay, cut back in after the 1, 2, 3 and pause. 1, 2, 3. So then this is k1, k2, then the system of equations is 0 times k1 plus 8 times k2 equals 0. Well, obviously, then k2 is 0. And k1, we don't have enough information to determine, so it could be any number, so I'll just call it k1. So now to form the eigenvector, we don't want to just call it any number, because when we find these eigenvectors, every eigenvector will have at least one parameter. And so what we do is we choose convenient numbers for those eigenvectors. So instead of k1 equals k1, when I form the eigenvector k1, I will say that this is the vector 1, 0. I know k2 has to be 0, but since k1 can be any number, it's convenient to choose the value 1, because that makes it easy to write down. And that should make a lot more sense when we do the next eigenvector. You'll see why that is. Okay, so this is k1. We've got that. So now let's find k2. So k2 is associated with lambda 2, so we have this equation a minus negative 5I bar 0. So a minus negative 5I is going to be 4 minus negative 5 is 9, 8, 0. Negative 5 minus negative 5 is 0. Bar 0, 0. So from here, we can form the equation 9. So we'll also do k2 is k1, k2. We just need to make sure we don't mix up the k1s and k2s between each eigenvector, but that should be pretty simple. So 9 k1 plus 8 k2 equals 0, which means that k1 is negative 8 over 9 k2. So if k1 is negative 8 over 9 k2, when we form the eigenvector k2, we want to put in numbers. We don't want to have k1, or rather, negative 8 over 9 k2, k2. We want to put in actual numbers. So what we'll do is we will let k2 be negative 9, then k1 is 8. And so our eigenvector k2 is 8, negative 9. So then if we summarize everything at the bottom, A is 4, 8, 0, negative 5. The eigenvalues lambda 1 is 4, lambda 2 is negative 5, and then the eigenvectors are k1, which is associated with lambda equals 4, is 1, 0. And k2, which is associated with lambda equals negative 5, is 8, negative 9. And so we have found the eigenvalues and eigenvectors of A.